range as well. This is decent. There's plenty of room in there to get up, to improve things. When you start coming into here, you have to start thinking about things like, did you get the homework problem 100%? Because that should be a gimme. That should be 10 points. When you get down into here, you start thinking in terms of, okay, at the end of the semester you can earn 100 points, 30, 40. If you're getting a 10 out of 30, that's going to mean that you're going to be wound up with a 30 or a 40%, 30 to 40 out of 100. It's kind of hard to get a passing grade with that. That's impossible. I've never done that. So that's where if you're down into here, you have to do some serious thinking about, okay, how can I really do much, much, much better? And the first place is to come to office hours with mine and my TAs. That's a great way to do it. The other thing is, remember when you do the homework problems, think about how they're going to be presented on the test. You're not going to have the solution sets to just study. You're going to have just the problems. And so you better be able to go from there in a blank piece of paper and fill that blank piece of paper, to perfection. So, and then I think, frankly, if you do a good job on the homework, the other ones fall in line as well. The other thing is, the other problems, now that you see them, the other problems come right out of the notes. But they're a little bit harder or a little bit different than what comes out of the notes. So the convolution examples were not terribly different from what we did in the notes. In fact, the Fourier Series and the Fourier Transform problems were exactly from the notes. And so, again, those should have been fairly straightforward, at least from my perspective. There was a really nasty question that counted all of 1 point on the test. And I just wanted to, because I'm proud of it, I wanted to go over it. You may have forgotten the test, but I asked a question on convolution and correlation. And I gave you an x of t and an h of t, the impulse function response. And I asked the question, is this a linear time invariant device? And that was a very, very hard question because the answer is neither. The answer is you don't know. The answer is I didn't give you enough information. The answer is I have to assume it for the rest of the problem to make sense. Okay? And so that but I asked that question on purpose. Exactly that way because that's the kind of thinking that you're going to have as an engineer. It's not enough to say, you have to have some judgment in there. You can't just say, well, I'm going to turn the crank and do the calculation. What you have to do is you have to say, I'm going to interpret my results. I'm going to be sure of the assumptions that go into my results. And the phrasing on that is very similar to what you might encounter in a real life problem. How do I know that this is linear and time invariant? Well, the chances are it isn't linear and time invariant, but you hope that over the range of the problem that you're doing, over the voltage range and the time range that you're doing, you can approximate it as such. Okay? So that was I wanted to mention that at some level that was an unfair question, but it was worth exactly 1 point out of 30, and I thought the value of the educational value in that was very sound, and that's why I asked it. And so that was the learning point. Okay. All right. Any comments, questions, gripes, things of that nature? Anybody wander in and need an exam back?
Jesse. There you go. Yeah.
Anybody else need one? Anybody else? All right. Welcome back from spring break. I hope it was a good one. I hope it was a relaxing one. I hope you got up on some of the homework from your other classes, because I figured you're pretty much caught up in this class. It's Monday. It's St. Patrick's Day. It's March 17th. We have, let's say, about 3, maybe 4 lectures to go on AM, and then we get directly into FM. And the 3 lectures that we have are going to be today's lecture, which is on signal sideband AM, and it's a set of mathematics that I think is among the hardest in the course. I think the mathematics that we're going to do today are going to be are about the most challenging that we're going to face in the course. Not so much the interpretation of it, because I don't even think you should really necessarily try it that hard, because the math is what the math is. But the interpretation, but the actual manipulations of the mathematics is tricky and difficult, and I'm going to walk you through it. I'm going to walk you through it in the frequency domain because that's how it's applicable for AM for the amplitude modulation problem that we're doing. When we come back on Wednesday, I'm going to repeat that complicated, difficult mathematics, but I'm going to do so in the time domain. And I'm going to do so with a completely different application in mind. And we will use exactly the same math, so it'll be just a review of the same manipulations. A little bit different because the notation will be different. The interpretation will be different. And what will come out of it will be a really nice mathematical result that you've probably observed before, but never really thought much of it or never did the fundamental theory for it. And it fits so well into side by side with AM SSB that it's worth an extra lecture to go over with that. Then we'll next Monday we'll tie both of them up together. Any loose ends, any spillovers that we have, which invariably we will. And then we're going to do the mathematics behind what the book calls vestigial sideband. But I'm going to present it in a way that's the same mathematics, but in a much more interesting and much more widely applicable sense. Okay? All right. Shall we begin? Any questions? We all awake? Yes? Oh, the screen. Yeah. Good job. Okay, we'll put the screen. That's on, and we'll lower it. There we go. Sorry, I meant to have that up for the whole preamble of the lecture. So if you're numbering it, we're on lecture 13. This lecture will also be on course echoes as well as Wednesdays and next week's and so on, hopefully to the end of the semester. We're going to do single sideband AM today, and this is Monday, March 17th. So, welcome back. Time to get into it. We have been talking about amplitude modulation of a message signal, M of t. Okay? As I've mentioned many times before, M of t is a random signal in time, but we do know something about the frequency range, the frequency behavior. And so on average, or over a long period of time, we know something about the frequency. So much of our design and development and analysis takes place in the frequency domain for this reason. And the way I've been drawing this is with some sort of hard limit of frequency. Make sure I label my axis. Oh, this is omega. And so I know that this bandwidth, maybe 2 kilohertz, maybe 3 kilohertz if it's voice, and so that's my amplitude. And over time, it wiggles all the way around inside of there. So I may or may not have this frequency content for all time, but in general, I'm going to make this excursion. And this is symmetric because it's a real voltage. And the symmetry here means that there's a redundancy of information. When I take my carrier, my local oscillator, my carrier, and I modulate this, amplitude modulate this, I move the whole spectrum out to plus omega c and minus omega c. I'm using up twice the bandwidth that I need to. Twice the bandwidth that I need to reduces the amount of revenues that I get for the bandwidth, for the amount of spectrum that I own. And it also brings on all kinds of impairments. There's many kinds of impairments that scale with bandwidth. The fatter the bandwidth, the more dispersion you have. It's the frequency. You have to line up the speeds of propagation of all the different frequencies inside of this. So if I now have this twice as much frequency, I've got twice as much dispersion, and I can't go as far. So if I can shorten the frequency content, I can either carry twice as much traffic, or I can go twice the distance. Which is, if I'm trying to cross a geographic boundary like an ocean, that's a big deal. Okay, so we're motivated to use half the bandwidth. We're motivated to use half the bandwidth. And because of the symmetry, I'm going to look at half of the signal, and I'm going to call that the upper sideband, USB. And I'm going to label this M plus of omega. So plus, upper, sideband, and then the capital M of omega comes out from the fact that I'm looking at my message signal in the frequency domain. If this is the upper sideband, what do you think I'm going to call this guy? The lower sideband, LSB, lower sideband. And what notation would I use if I'm using capital M plus of omega for the upper sideband? Capital M minus of omega for the lower sideband. Okay, good. So now you're thinking and you're getting comfortable with the notation. It's funny, in an engineering problem, in a theoretical problem, a lot of times just coming up with the right notation helps you through the problem. You know, so if you spend a moment doing a problem you've never thought of before, or you've never seen the answer before, you might think a little bit a priori about the notation that you use, because sometimes the very notation will influence the direction that you take the problem. And this is no exception. Okay. Let's see. If I have m of t going to m of omega, and I've introduced m minus of omega and m plus of omega, it seems to me that I would also consider m minus of t, that is the Fourier transform of m minus of omega. Okay? In other words, if I just have this lower sideband, and I inverse Fourier transform it, I'm going to get an m of t. It'll be complex because it's not symmetric. Complex means that I know information about the phase. Good. The phase of the signal. Okay. So if I have a real signal, I'm going to have both sides symmetric. If I now truncate that or cut that off or cleave it right down the axis, I'm going to introduce a phase-dependent part, a phase-dependent information, phase information, and so it'll become complex in m of t. Okay. And by the similar notation, if I have my upper sideband as m plus of omega, I should at least mathematically be able to inverse Fourier transform that, and I'll have m plus of t. Okay. Does that seem reasonable? So one of the things that I'd like to know is what the heck is m minus of t and what the heck is m plus of t? What does that look like? And the first thing I note is that the lack of symmetry in the upper sideband and lower sideband implies complex m plus of t, m minus of t. Okay? So that's the first observation that I make. Okay? Now the other thing I can say, the other thing that I can say is that m plus of omega plus m minus of omega that's this guy plus this guy, that makes up this whole capital M of omega. Does everyone buy that? Okay. And if this guy Fourier transforms to M of t, and remember that M of t obeys superposition, remember Fourier transforms obey superposition, then this guy here will Fourier transform to M minus of t. This guy here will Fourier transform to M plus of t. And I should be able to add those together to get M of t. Okay? Now let's do some thinking about the symmetries here. Let's do some thinking about the symmetry here. M of omega is symmetric. M of t is real. It's a real voltage. Okay? It's a real voltage signal. M plus and M minus by themselves are asymmetric. And so M plus of t and M plus of t and M minus of t have complex parts. How on earth do I take M plus of t, which is complex, M minus of t is complex, and get M of t, which is not complex?
You know that the
complex conjugates. Complex conjugates. The complex parts have to cancel out when I do this complicated mathematical operation called addition. Okay? So that's exactly right. So there's something deep and nice about that, and that's going to be our leverage. But before we get there, let me do one other thing for you guys. Redraw my figure. There's my M of omega. And what I want to do to get my M plus of omega, I always think of this as I have this kitchen knife, and it's a big cleaver, and if I'm like cutting a vegetable, I chop it down, and it's a nice knife, so it just splits that zucchini right in half, right? And so I want to do the same thing, a nice, clean, perfect cut on this function to separate out the upper sideband from the lower sideband. And so what I want to do is I want my cleave to do something like this. Okay? I want that cleave to do something like that. So I want to be able to keep my upper sideband, multiply it by 1, and I want to get rid of my lower sideband, chop. And I want that to go to 0. So what is the red function that I've just drawn? Perfect. Do they exist? Does a perfect cleaver like that exist? No. Even my really nice, expensive kitchen knife has a thickness associated with it. And then when I slam it down, I may slam it a little bit tilted and not quite perpendicular. So there's a lot of error in all that. But that's pretty much what we're saying here. And so 2 more mathematical facts to know and to share. M plus of omega is equal to M of omega multiplied by the step function. And here we're working in the frequency domain. So see, I actually messed that up myself. I'm so used to thinking of U of t, but I forgot that I was in the frequency domain. And so I wrote erroneously U of t instead of U of omega. Okay. And then now, to cleave, if I'm interested in the lower sideband, what I'm going to do is I'm going to flip or reflect U of omega. And so I'll write that as U of minus omega. Okay?
So, like when you add them back together to get m of omega, once you get like double at omega 0?
Right. So, well, I've got to worry about that, right? I've got to worry about that. It turns out that it'll still survive because this guy here will be exactly this one here. This is a separate guy here, and remember, u of minus omega doesn't have parity, right? So I can't factor out one or the other. U of omega plus u of minus omega. Well, actually, let's do that. Might as well just do that. M plus of omega plus m minus of omega is equal to m of omega. I factor out an m of omega because that's what you're worried about. And now I have u of omega plus u of minus omega. And this guy here looks like that. This guy here looks like that. So these guys don't cancel out to 0. This guy says if you're less than omega equals 0, you're 1. This guy says if you're greater than omega equals 0, you're 1. So what does that bracket equal?
1. I just thought you had a double value at 0.
Yeah, that's really good. I'm an engineer, and so it's very, very, it's correct mathematically to stress out about what happens exactly at 0. As an engineer, I choose not to. But let me tell you some history here, okay? Pardon?
So it just doesn't matter.
Well, let me give you a couple of ways of thinking about this. There are a bunch of different math textbooks and a bunch of different engineering textbooks. I have seen, I don't know if Lattice does this, I have to check, but I have seen where u of omega is equal to 1/2 exactly at omega equals 0. And if that's the case, that sidesteps your worry because I get half of the 0 value and I get half of the other 0 value. And then the other way of thinking about it is it's undefined at 0, but it's defined at one is defined at 0 minus and one is defined at 0 plus an epsilon. And we just take the limit as those guys go to the center. And in that limiting process, we recover everything. Again, from a practical implementation, we're trying to do a coding theory. We're trying to realize a system here. What we're really, we don't have a prayer of realizing u of omega. If I told you to design that filter response, you'd have to keep adding zeros and zeros and zeros, or keep adding poles and poles and poles to get that sharp rise. You'd never get there. So we, from a theoretical perspective, we can fix things with the right definition of u. From an engineering perspective, we just have to recognize that of all the problems that happen with this cleave, maybe that one is, maybe it's all rolled into one. Okay, so we've got a theoretical problem that we can fix, and we've got a realization or an engineering problem that we're going to have to really think about and really work on, regardless of what the math says. Okay. Good question, though. I'm glad. Oh, I also wanted just to go through this because this, sometimes I've noticed that this these little things kind of can confuse you. Parity happens. All right, so let's go on, and I'm going to write things again that we have done before. Okay, so the Fourier transform is a linear transform, and so this has to hold. And we decided that m plus and m minus were complex conjugates of each other. And those are of t. And so I have m plus of t Okay?
And what is that penalty?
That's m little h, m sub h of t. And just so there'll be no confusion, H stands for a mathematician's name, and it's called Hilbert. Okay? It's not the impulse response, for example. If I add these guys up together, I have m plus of t plus m minus of t. Notice the first term is 1/2 m of t here plus 1/2 m of t here. That gives me m of t. And then on this term I have j mh of t minus j mh of t. The second term is 0. Okay? So, from all this, we need to find whatever the heck that mh of t is. So we'll start with what we know, which is something about the frequency content of the signal. That's m of omega. I want to be neater about my h's and my pluses. Yell at me if you can't read them or even if they seem a little bit unreadable. Okay? So I start with what I know, which is m of omega. I already understand that I need to cleave it as sharply and tightly as I possibly can to get my m plus of omega. The small thing I'm going to change on this, just to make things a little bit cleaner, a little bit nicer, is I'm going to get rid of that u of omega. That u of omega step function, you've been working with it forever and a day. It's a great function, especially setting up the problem. But when we start to do Fourier transform stuff with it, inverse and forward and backward Fourier transform, then we get a headache because it doesn't have parity. It's neither odd nor even. Right? And so there's a way of writing the step function in terms of the even part and an odd part. This was a homework question. In fact, it was this was part of the homework question I asked on the test. It was a coincidence. I'd like to think I'm that organized, but I'm really not. But it is an important one, which is why I ask it a lot. So m of omega, and then this is u of omega, divided up into its even part, just a constant, and its odd part, the signum function. The signum function. Okay? So this guy has definite parity. Are we comfortable enough with the signum function that we can see where the connection between there and there? Let's go ahead and draw these guys then. There's my omega, and I'll start with the signum function, which is +1 and -1. And this guy here is the signum function of omega. That's if you ask to graph signum of omega, this is what you'd graph. It's -1 in the negative frequencies, negative omega, and it's +1 in the positive frequencies. Okay? I'm going to add 1 to it. When I add 1 to it, this branch becomes a 0. This branch goes up to +2. So this red line is 1 plus the signum of omega. If I multiply by this half, this guy does nothing. This guy pops back down to 1. And I have u of omega is equal to 1/2 of 1 plus the signum function of omega. Okay? Okay. So that's a review of, and again, what you might do is work this, leave a little space, and work this whole thing out with t's instead of, so you have what is u of t, what is 1/2 times 1 plus signum of t. We'll be doing that on Wednesday anyway. Probably not in quite as much detail. Okay. There's one other fact. There's one other fact about all this. And I won't prove this, but there's a Fourier transform pair. It's actually in table 3.1, I think. And hopefully I have my minus signs right and the location of my square root of -1's right. But there's a Fourier transform for a signum. And that Fourier transform for that signum is 1 over pi times t. 1 over t. So I can multiply both sides by j. And that clears out the -1. So j over pi t is the Fourier transform of signum of omega. Minus 1 over j pi t. It's like I can play all the games I want with that 1 over j and minus signs. So that minus j will pop us around a little bit. So don't get too stressed out about it. Okay? And I want to just plot 1 over pi t for you real fast. It's kind of unfair because there's a complex number in there. But there's my 1 over t dependence in the time domain. And look at what happens right at 0. If I want to build a filter with this response, if I want to build a filter with this time response, with this h of t response, with the impulse function response, what I need is a box full of electrical components that if I kick it with a delta function, shoots up to infinity, and then immediately rolls down with a 1 over t. So a delta function response on this is going to give me an infinite, for an instant of time, an infinite. It's a singularity. So I have the step function singularity. I have the step function singularity in the frequency domain, and it's got to go that 0, that omega minus omega plus, what happens exactly at omega equals 0 issue that you raised, has got to go somewhere. Mathematically, it goes to the singularity in the time domain. Okay? So with this, if you have to realize this, you know that that's an ill-posed problem, and you'll never be able to build the perfect filter that does this. The best you can do is say, well, I'm only going to care after a millisecond or a microsecond or a nanosecond or a picosecond or a femtosecond or an attosecond. Yes, sir.
You just mentioned before, I think, that you said J over pi t transforms to just sigma most omega. But is that what you said?
Well, okay, so the Fourier transform pair that I've written is minus j signum of omega goes to 1 over pi t. Okay? And so I can multiply both sides by j, and I'll have minus 1 times minus is a positive 1, and then I'll have a j on this side in the numerator.
You can just do that?
Well, you can prove it. It's a Fourier transform, right? So I'm multiplying through by a constant.
Okay.
Right? Yeah. That's okay. I mean, I'm sorry. It's a really good question because you know the answer, right? When I said you multiply by a constant, you said, oh, of course. But then you had to think, but you have to remember the constants can be complex, and that's so get you have the knowledge, but now you're going to get comfortable and assertive with your knowledge. You're going to get confident about it, and that's my job. My job is not just to give you the knowledge, but to make sure that you're confident enough that you can win an argument. This design will work because, not because I'm the boss, or not because I say so, not because I'm the professor, but because this is the rules of the mathematics or the rules of the circuit theory or what have you. Right? It's not enough to be right. You have to communicate and convince people that you're right. You have that. Just have to practice it. Okay? It's empowering, I hope. Okay. Now, where were we? I think one of the things that makes this derivation hard is that there's a lot of lagniappe. There's a lot of extra little pieces of the puzzle. And so we have to stay focused. We have to stay on track. And remember, what we were doing was we were taking this upper sideband. We were taking this upper sideband, m plus of omega, which is equal to 1/2 m of omega times 1 plus signum of omega. M plus of omega, and I'll just rewrite that just slightly differently. I'll multiply it through by m of omega. And I'll write it like that. Okay? So this is nothing more than m plus of omega is equal to 1/2 m of omega times 1 plus signum of omega. M of omega is 1/2 of m of omega plus 1/2 of m of omega times signum of omega. Okay? And the other thing I know there's not a lot here. Oh, yeah. The other thing I know is that m plus of t is equal to m of t of 1/2 m of t plus j mh of t. So if I write this guy here, I have my m plus of t. This guy goes to 1/2 of m of t in time domain, right? This stuff we've established, and this stuff was the very, very beginning of our weeks ago, actually, months ago probably. And then I also have this last guy here, which is 1/2 j m sub h of t. So what we wanted to do is we wanted to find what the heck mh of t was. And now I see it as the Fourier transform of m of omega times the signum function of omega. So, I know that mh of almost wrote T. Pardon? So I have mh of omega, that's in the frequency space, is capital M of omega multiplied by signum. And this Fourier transforms to mh of t. And this guy is, whatever the Fourier transform of this, m of t, convoluted with whatever the Fourier transform is of that. Remember, a product in the frequency domain is a convolution in the time domain. You actually think of it as a convolution in the time domain is a multiplication in the frequency domain, but we're going the other direction now. So I have this guy here, and the inverse Fourier transform of this guy, or minus j times that guy, is 1 over pi t. Okay. Fourier transform pair. So now, here's our filter response. And so I see that to generate mh of t means that I built a filter with this impulse response, and I take my m of t and I send it through. Whether this works or not depends on how well I can realize that non-physical filter. Okay? And don't get discouraged that it's non-physical and therefore impossible to do a perfect job on, because you can do pretty close. You can get pretty close. Right? You'll take a hit, but you know, one way to think about this is, if the problem happens at omega equals 0, what do I do to sidestep the problem? Pardon? So if I have a problem with what's happening at omega equals 0, what component is that? That's my DC component. If I told you that I didn't like my DC component for some reason, like my filter threw up on it, what would you do? You would what? You would add a capacitor to do what? To remove the DC component. You'd add a DC blocking capacitor in series, and just say. The other nice thing about that is it makes your signal even, or rather symmetric around the time axis. Okay. So there's ways of doing this, right? Now let me just state kind of the obvious here. M of tau, that's my dummy variable. T minus tau, d tau. There's my convolution integral. There's my convolution integral. And this is called the Hilbert transform. Okay? So when people talk about the Hilbert transform, what they're talking about is this integral. And this integral we recognize as a convolution from our training. From our training, we recognize it as a convolution of the signal, m of t, that's the message signal, with an impulse function response h of t equal to 1 over pi t. So, if I have this m of t, and I want to get out m plus of t, and I want this to equal 1/2 m of t plus j mh of t, I need to put a system in place to do this. This will give me my upper sideband in the time domain. If I Fourier transform the output of that signal, it's the frequency domain, m plus of omega. I'll do half of this circuit for you. I'll do the easy half, my prerogative. So the first term is 1/2 m of t. So I'll just go through a resistor network, an attenuating amplifier or a resistor network, to give me 1/2 of m of t. And what should I do on the bottom one? What should go on the bottom one? Remember, I want mh of t. And remember, mh of t is m of t convoluted with 1/pi_t. I think I need a 1/2 in here as well. Well, I think we're overthinking this. So let me just multiply by 1/2, and then let me send it through a filter with h of t equal to 1/pi_t. Okay? So realizing this filter, if I can realize this filter out of capacitors, inductors, resistors, op amps, diodes, whatever I need, or a DSP. That sounds even better. Then I can go ahead and realize this. This is all in the time domain, right? So that's our system block diagram, for those of you who like to think about that. So if I can use a Hilbert filter, here's how I can realize signal sideband AM. Okay, so what do I mean by a Hilbert filter? And in the time domain, the impulse function response is 1/pi_t, which looks like that. Better? Sorry. Okay. In the frequency domain, which is sometimes a little bit easier to plot, it's minus j signum of omega, or 1/j signum of omega. Signum goes -1 to +1, right? It starts out at -1 and then it flips to +1. I multiply it by minus j, and so the 1's become a j, complex. And then I have that minus sign to worry about, which is a flip, or flip that way, I guess. And so if I plotted this, that's what this guy looks like in the frequency domain. But that's a hard notate. That's a hard way to visualize it. So let's look at the magnitude of h of omega. And that says I take the real part squared, I take the imaginary part squared, I add them together, and I square root them. Well, the real part is 0. Excellent. The imaginary part, 1 or minus 1, squared is 1. So h of omega, the magnitude, is equal to 1. And if I plot that, I have that amplitude. I have that. Does that give anybody heartburn? Does that surprise anyone? You can follow the math, right? The math was not, it was just bookkeeping. I remember that the magnitude of h of omega is the real part squared plus the imaginary part squared. Looking at h of omega, there's no real part, so that guy goes to 0. The imaginary part was 1 or minus 1, 1 or minus 1. Square that, I don't care. Square root it, I don't care, so I get the magnitude is a 1. So mathematically, I'm okay. Mathematically, I checked my work, and that's the answer. This is a special kind of filter. Whatever frequency I send us, whatever frequency I put in there, the magnitude doesn't change. I don't select, it's not low pass, it's not high pass, it's not band pass, it's all pass. It's called an all-pass filter. Every frequency is treated exactly the same. A C is the same as an A sharp, is the same as a D. Any chord on my guitar, can you not see this?
When would you use an all-pass filter?
I'm getting there. Actually, that's a great question for you.
If it's all pass, then why even have it?
So think about this, right? Think about what I'm trying to do here. I have a message signal, M of t. I have a message signal, M of t. And that maybe that message signal is, where's my guitar player in the audience? Whatever note you play on whatever note you play on a guitar, you value each and every one of those notes. You don't value, what is it, an A more than a G? Give me 2 chords.
I guess like C sharp diminished. I don't know, you have a million chords, but yeah, or just C major.
Okay, so you value a C major the same as a C, whatever, right?
Yeah.
So you're strumming just as hard depending on whatever position your fingers are in. You care about one. You love one chord just the same as another chord. And that's very common in a communications problem. If I've got a deep baritone voice and I've got a squeaky baritone voice, they're both paying customers. I don't want to diminish one versus the other. So I want to treat both of those frequencies as exactly the same. And that's the first value of what an all-pass filter does. Is whatever I do, I treat every frequency the same. And in a communication channel, there's a lot of need not to bias one frequency from another frequency, not to make one go away and one stay around. So all-pass filters potentially have their value. Okay? Now you're still scratching your head saying, well, I didn't do anything to the signal. Who's saying that? Are you saying that I didn't do anything to the filter, the signal?
No, it's an amplitude modulation, isn't it?
I did nothing to the. Who says I did nothing to the signal? Come on, don't be shy. Who says that I potentially can do something to my signal? What parameter have I not looked at yet? Phase response. I've only given you. Here's my h of omega, right? It's made up of a magnitude and a phase. The magnitude part of it is the easy part of it. The magnitude part, I still have a chance to mess up this signal by messing up the phase. And if you think back to the problem of the signal sideband and compare it to the QAM, both of these frequencies, it stands to reason that shaving our frequency in half is all about phase. The complex part of the fact that m plus of t is complex is about phase, right? Not magnitude. So all-pass filters are very, very useful in comm systems because they allow you to keep all the frequencies but juggle around their phase, juggle around their delay through the system, their relative delay through the system. One of my favorite all-pass filters has to do with echo cancellation. Okay? If you think about an echo on a line, you send out a hello, and what comes back is hello, 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 hello. The frequency content of each of that hello hits you at time t equals 0, twice the round trip of the transmission line, once times the round trip, twice times the round trip, 3 times the round trip, and so on. What you'd like to do is take all that information, all the frequency content in the word hello, and slide them all back again at time t equals 0. So that's a phase or a time delay problem. So let's go on and do the other half of the problem. The phase of h of omega is the inverse tangent of the imaginary part over the real part, right? And I have, the real part is still 0. The real part is still 0. So we're going to have to scratch our head about that. Thankfully, the inverse tangent function is a funny function. Has a singularity already, so that's kind of nice. And this imaginary part here is either 1 or minus 1. So what we're looking at is the inverse tangent of 1 over 0 versus the inverse tangent of minus 1 over 0. And if I remember my inverse tangent, there's a nice swing between minus pi and pi, minus 90 degrees and 90 degrees. And if I translate this into my frequency, then I'll have pi over 2 for my negative frequencies and minus pi over 2 for my positive frequencies. So a Hilbert transform, Hilbert filter, is a constant magnitude and a minus pi over 2 phase shift for all positive frequencies.
Back on the echoing part, how would you get a signal to even have an echo like that without it going through a filter?
Well, so the filter is actually the transmission line. So if there's a link of BNC cable between us, that's what, about 15 feet? So that's about 20 nanoseconds. So as I say hello, you hear the hello in 20 nanoseconds. It comes back. If I have a mismatch of impedance, there'll be a reflection. It'll come back to you, and you'll hear another hello in 40 nanoseconds, another one in another 40 nanoseconds, and so on and so on and so on. Okay? So that rattling around of that word hello in the transmission line is the echo. If I take it at if I'm at your end and I know that I characterize that filter, I grab the H of T and I grab the hello and I put it back on top of itself. Keep maybe 3-4 of those hellos. I've captured most of the energy in all the echoes. And you hear it delayed, but you hear one hello. So I build the inverse filter of this transmission line in DSP, for example. Okay, it's it's just to show off a little bit. It's called the lattice filter. Yeah, it's called the lattice filter, and there's a nice algorithm for realizing it in DSP. Okay. And just again, this was a real problem before DSP. I remember, if I was living in the States, my parents might be living in Holland when I was in college, or so on, or in grad school, and I would give them a call. And the round trip time across the transatlantic cable was such that I would say a sentence, and there would be a transit time. It would come out at the other end, and my sentence would echo back almost exactly overlapping with my parents. So I would hear both my question and their answer right on top of each other. And you had to really struggle as a user to slow down the pace of your conversation so you didn't have this complete overlap of your... Yeah, that was in the 80s. A lot of bad things happened in the 80s. Echoes on transatlantic cables being just one of them. Okay? Let me do a quick example. And by this example, by the way, is how you could approach. This gives you an idea on how to approach every function. So, the Hilbert Transform, and I'll write this as a mathematician, not to confuse you, but rather just to give you a different notation, because you're going to run across different books. So I have the function, or I have the signal f of x. My dummy variable is x prime. There's my convolution. And let me just say, for example, supposing my signal f of x prime is equal to one of our favorite functions called the cosine. Well, we know that the Hilbert function, the Hilbert filter, is a phase shift for all frequencies. Here's my function. It exists at a particular frequency. So the Hilbert transform of cosine is going to equal the cosine of x prime minus pi over 2, which is equal to minus the sine. You should double check that minus sign. Double check that minus sign. Okay, but it's a sine of x prime. So the Hilbert transform of a cosine is a minus sign, a 90-degree phase shift. And similarly, the Hilbert transform of sine is a cosine, positive cosine. So one way to do a Hilbert transform is to take an arbitrary signal and do a Fourier series, So now I've represented that signal as an infinite sum of sines and cosines. All the cosines become minus sines, and all the sines become become positive cosines. And that would be the Fourier transform of that generalized signal. And the Hilbert transform. That would be the Hilbert transform of that signal. Okay. So that's another interpretation of what we mean by an all-pass filter with a 90 degrees phase shifting going on. Okay. Now the last piece of the puzzle, and I better check my time. Yeah, perfect. Last piece of the puzzle is the use of all this in AM. So I do M of t. I mix it with a carrier. I want this guy here as my upper sideband. And on this guy here, on the negative frequency part, it turns out, see this guy, I want the upper sideband. That's the higher frequency components in the positive, and the more negative frequency components in the minus sign. That's this guy there. So this becomes my upper sideband, and this becomes my upper sideband signal. So the upper sideband of omega is m plus of omega minus omega c plus m minus of omega plus omega c. Have to think through that a little bit. That's a little confusing, but I want to grab this part here and this part here to get the information that I want. In the time domain, I'm going to take m plus of t, the Fourier transform of this, and mix it. And I'll write it in the complex because I'm already have a complex m plus of t. And then I have and then m minus, and again I mix that with a minus j omega ct. Now, m plus of t is equal to 1/2 times m of t plus j mh of t. M minus of t is equal to 1/2 m of t minus j mh of t. M plus of t, m plus of t, m minus of t, m minus of t. MH M of t is real. MH is real. So I have MH of t plus j, MH of t, and then I have this e to the j omega t. I've got this e to the j omega t minus j omega t. When I break this e to the j omega ct into cosine and sine, and this into a cosine and sine, then what I learn is that I have that. So leave a couple of lines in your notebook. Substitute this MH, this M plus, and this M minus into this expression. Work through all the J's, the Euler's relationship, and it'll simplify down to that. And then for even more fun, you can show that. So now, if you want to realize this, and this is much more careful analysis than what we did before. We were kind of sloppy. This clears that up. Hilbert filter, mixer, delay, local oscillator, mixer, sum, and this is psi USB of t. Whoops, better be able to see that. And that's all what this red line says. Oh, this is a local oscillator? Cosine of omega ct. Thank you. Apologize for that. And then this is a phase shift to give me a sine. Very much like what we did with the QAM. Okay. So this part we ripped off of the QAM, and this part is the Hilbert. And this gives us our upper sideband. Take our message signal and code it that way. And we're not done. If I mix this at the end to demodulate, that's of t, and cosine of omega ct. This is going to equal 1/2 of m of t times 1 plus the cosine